Okay, ma'am, we can start.
A very good morning to everyone present out here. I, Nikhat Mullah, would like to welcome all participants on behalf of the organizing committee at Bharatiya Vidya Bhavan's Sardar Patel Institute of Technology to day 3 of AICT-sponsored 2-week online FDP on insights into intelligent automation, machine learning, and data science, foundations of data science. To begin with, I would like to start with this quote by John Tukey. Be approximately right rather than exactly wrong. Today's session discusses exactly this point. The topic for today's session is statistics for data science. Statistics are very important for observations, analysis, and mathematical prediction models. Today's session will provide us a detailed overview on various statistical concepts and techniques. I would now like to take this opportunity to introduce our speaker for today's morning session. Today we have with us Dr. Vishwesh Vyawahare. Dr. Vishwesh Vyawahare is professor and head of Electronics Engineering Department, RAIT Mumbai. Dr. Vyawahare has completed his PhD in Systems and Control Engineering from IIT Bombay. He has worked as a project research scientist at IDP in Systems and Control Engineering, IIT Bombay. He has published more than 70 papers in various international journals and conferences of repute. He is also a branch counselor for IEEE RAIT. His research interests include power electronics, systems, and control. Dr. Vishwesh Vyawahare, I wholeheartedly welcome you to this FDP. We look forward to an enjoyable mathematical statistical session conducted by you. May I now invite Dr. Vishwesh Vyawahare to kindly take over from here and start today's session. Thank you.
Thank you, madam. At the outset, I would like to thank Department of Electronics Engineering, S.P.I.T, especially Professor Rathore sir, for inviting me to deliver these sessions. Thank you, sir, for inviting me. Now I would stop my video because that would take the bandwidth, and I would like to share my screen. I hope my screen is visible.
Yes, sir.
Yeah, thank you, sir. So, dear participants and colleagues, the session that has been allotted to me is statistics for data science, and of course machine learning also, and some part of tensors. So when Rathore sir discussed with me that I have to deliver these talks, I started pondering whether I should go with the conventional PowerPoint presentation or Beamer presentation, and I should go ahead and present it. But then I realized that it would be slightly dry. I have to teach you statistics, I have to teach you probability, at least I have to give you a glimpse or a flavor of statistics and probability. And we know that if we teach these subjects through a presentation, then it becomes very dry, at least that is my experience. There might be speakers who can teach very well with the help of a presentation, but then I realized that why can't we go closer to the classroom teaching? And that's why I decided that I will not prepare any presentation. I will be rather using this Microsoft whiteboard, and I would be teaching you, or we all together will be learning this statistics and probability. Also, one more thing I would like to tell you that since we have been going ahead with statistics and probability, I thought that giving you a superficial introduction to these two topics, especially probability, wouldn't be a good thing. Okay, just excuse me for a moment. Okay, so it would not be a good idea to give you a superficial introduction to this. So I decided that I would give you a slightly rigorous mathematical exposure to the probability. So we would be going ahead with the set theoretic approach to probability, and then after defining what is probability, what are events, what is the sample space, okay, and then going ahead with the random variables, then we will go ahead with this our standard deviation, mean, mode, median, and all those things. Okay, so this is what I'll try to follow. And last but not the least thing is, please excuse me for my handwriting, which I will be putting on this Microsoft whiteboard. I'll try my best. My handwriting is not so good, but I'll try my best to at least make it legible, and I hope you will able to understand. Okay, so let us start. So we will start with statistics. I hope it is visible to all the participants what I am writing on this Microsoft whiteboard. Okay, so what is this? It's a branch of mathematics. It's a branch of mathematics. What does it do? It is a tool for analyzing data. Okay, so we should remember these two important things, that the most important thing, it's a branch of mathematics, that's fine, but it's a tool that is used for analyzing the data. Okay, now as per our contents, and there are a lot of you can say anecdotes, there are a lot of facts and interesting things about statistics. In fact, I will be presenting day after tomorrow at the end of my session. When I will end the statistics, I'm going to present you a very interesting case where the data is totally different, but the mean, mode, median for all the three sets of data is equal. Okay, so most important thing here is, it is very deceiving, okay, if not used properly. Very important. So it has to be used very properly. We should understand the basics, fundamentals, and all those things. Okay. Next thing is very important. Machine learning and data science, because in data science as well as in machine learning, you are dealing with data. Okay, and if you want, and the data that you have, you don't have any control over that data. Okay, so you need to reshape that data, you need to condition that data, and then you need to bring it into a form which can be used to draw inferences. Okay, so the statistics and probability are very important for machine learning and data science. Okay, we will slightly move ahead. So as we all know, there are two parts. One is descriptive stats, okay, So what does this do? This summarizes raw data, okay, into a form that can be very important. So what does this do? It summarizes basically the descriptive statistics. Statistics is basically divided into two parts: descriptive statistics and inferential statistics, or descriptive statistical methods and inferential statistical methods. Okay, right. So as the name suggests, this part of statistics is descriptive. So what does it do? It gives you, it describes the data, it describes the raw data. Okay, so it basically describes, okay, it describes this raw data, and it tries to make that raw data come into a format, okay, from which it can be analyzed. Okay, the second part here is the inferential statistics. Or inferential statistical tools. Okay, so inferential statistical tools. Okay, now here what they do, here what happens, what does this tool does? It basically, as the name suggests, draws inferences. Okay, or it also draws something called as conclusions. Okay, so very important. It draws inferences and or conclusions, basically. Okay, so what we have seen up till now, this is what we have seen. Okay, so we start with statistics, which is a branch of mathematics. Okay, and it is a tool used for analyzing data, receiving if not used properly, very important in machine learning and data science. There are two statistical tools, or two types of tools available in statistics, broadly categorized, okay, as descriptive statistics or descriptive statistical tools, okay, and inferential statistical tools. Okay, and these are the tools that can be used for analyzing the data. One is for summarizing the data and it can be made ready for analysis, that means it describes the data. Okay, and second one is to draw the conclusions. Now conclusions or inferences means which is the number in data that is mostly repeating, or which has got the maximum frequency, what we call it as a mean. Okay, and other thing, how much are the other values away from this middle value or mean value. Okay, and we go ahead with variance and all those things. Okay, so this is what is known as this. Okay, now next thing I would like to discuss is, and I should give you a motivation. Okay, so the next question that is very important is, so the question, why statistics is important in data science and machine learning. Why it is important in data science and machine learning. Okay, so we'll try to get some motivation for this. Okay, so as I said first, visualizing the data. That is very important. Okay. Second thing very important is for cleaning and preparing data. Okay, because if you don't use statistical tools, okay, you may be having a very raw data and you may need to clean a data, okay, and you may have to prepare the data for feeding to your data science tool or for your machine learning. Okay, so this is very important. And the last but not the least thing is these statistical methods, okay, right, they aid in choosing the model. This is very important. Okay, if you know what data is, okay, these things they can help you in choosing the model that your machine learning application wants to use or that your data science application might want to use. Okay, so these are some of the motivations that I would say very important for good motivation for statistics being important. Okay, fine. Next we move ahead. There are some basic definitions about these before we go delve into more in-depth mathematics, okay, because I will be shifting from statistics to probability. After this I am going to give you a detailed introduction about probability and then we are going to move ahead. Okay. The next most important thing is the some important terms that I am going to define now. Okay, the first one is population. Okay, what is population? Okay, so basically it is all possible observations. All possible observations. You can also call it as entire pool of data. Okay, so population, like for example, you want to analyze the height of say all the people in Andheri, for example. Okay, so that is your population. You have this data, you have the person's name and you have the height of that person in say meters, right? So that would become a big population. So it's all possible observations. Why I am giving you this example of Andheri is because then I am going to come to something which is very important, and the next important thing is nothing but sample. Okay. So the next important thing is sample. What is sample? Sample is a subset of observations. So you have these observations. Okay, right? Now you are talking about a subset of these observations. Okay. For example, if your population is height of all the people, okay, in Andheri, maybe sample can be height of all the people who are present in S.P.I.T right now, okay, or at some instant of time, right? That would be your sample. Now, the most important thing about statistics and all these things is that we can use this sample to draw inferences about the population. That is the most important thing, and that is what its beauty. So what is important is analyze sample, okay, analyze sample and draw inferences about population. That is very important. Is it possible that I would analyze the sample, I will do some statistical treatment to that sample, the data which is available in sample, okay, and can I get inferences about this? Okay, so this is what the statistics will help us in doing all these things. Okay, so let me give you some example. I think I have already given you an example of this. Okay, so just quickly, so I will have population on one side and I will have sample on other side. So first example that I can have is height of people or heights of people in Andheri, and the corresponding sample will be heights of people in S.P.I.T. That is one example. Okay, I can go ahead, I can give you a second example also. This is an actual data. Okay, this is an actual data, physical data that you have with you. You can also define these population and sample notions or concepts on hypothetical data. Okay, so this is 2. Okay, so number appearing on a dice. Okay, right, when it's thrown for 24 hours. So for 24 hours continuously you are throwing the dice, and correspondingly you are generating a set of data. Sometimes you get 1, sometimes you get 2, sometimes you get 3, and all those things. Okay, now what would be the samples for that? Okay, so the number appearing between 10 a.m. to 11 a.m. that can be my sample. Okay, so now you have understood the population and sample. Very important. Okay, we will move ahead. I am going slightly slow, okay, because we have to learn each and everything. There might be these things may be preliminary, and these things may be what you can say very trivial for a majority of the participants, but then we would start from the scratch and we would go ahead and we will try to understand the things. Okay, now the next most important thing is that, okay, in this statistics, what are the most important things, or what are the most frequently used uh, uh, frequently used tools for that? So I want to find out the mean of a data. Okay, I want to find the mode of a data. I want to find median of the data. Okay, I want to find the expectation, which is part of mean only. I want to also find something called as standard deviation. I want to also find in what way my data is distributed. Okay, and the most commonly used distribution is Gaussian or normal distribution. Okay, so Gaussian or normal distribution. Then I am also interested in something called as skewness. I might be also interested in the kurtosis analysis, okay, of all these. So there are two ways with which we can teach all these concepts. Okay, so what are these concepts? These are the concepts that I am talking about: mean, mode, median, expectation, standard deviation, distribution, okay, I mean which comes from the density function, okay, skewness, kurtosis, and all those things. These are some of the parameters, okay. When you talk about statistics, these things come to your mind. These are the things which are used. These are, so if you are given a data, let's say you are given a data of height of 100 people or weights of 100 people, okay, or the rainfall in Mumbai region for last 1 month, in the month of July and August, let's say, when there is a, when the rains are at their peak, okay, and you are given this data, and now we ask you to do the statistical analysis. The first thing that you will do is you will try to find out is how much is the average rain. Average rain. Okay. Now, when you talk about this average rain, immediately you come to this mean, average. Okay, so these are some of the statistical tools that everyone who wants to use statistics, he or she must know. They must learn this in order to do the statistical analysis of some data. Okay, right. So now what we are going to do, there are two ways with which you can learn this. One is, so two ways to understand and learn these concepts. Okay, one way is very simple, is superficial way. What is the superficial way of learning this? The superficial way of learning is you just open any book on statistics and you try to understand what is this, how do you calculate the mean. So they give you this simple formula, x bar, okay. So x bar is equal to 1 by n summation I is equal to 1 to or n, okay, xi. So xi's are your data, and you go from 1 to n and you try to get the mean. This is one way of understanding it. Okay, okay, it teaches us the tool. It teaches us the tool, okay, but let us try to understand what is this basically. Okay, so what we are going to do here, we are not going to follow this superficial way. Okay, what we are going to do is we are going to understand these concepts, okay, from probability point of view. We are going to understand these concepts from probability point of view, and in that too also we are going to go ahead with something called as set theoretic approach to probability. Okay, so we are going to understand this set theoretic approach to probability, and from there we are going to go ahead and we are going to understand all these things. So what is the advantage? What are the problems here? The problems here are, it is mathematical. Okay, first thing. Okay, it involves set theory. You need to understand set theory. Okay, you need to understand the basic concept of functions. Okay, so these are some of the requirements for this. So what we are going to do, we are going to go ahead with this approach, and I'm going to explain to you all. Some of you might be already aware of this, because if you open any book on statistical signal processing or statistical systems and all those things, you will find these as prerequisites. Okay, so the book that I'm going to follow is by Peebles. There is a book by Peebles. Okay, it is published by TMH. Okay, it's a very good book. There are other books available also. Papulis and Pillai is also one of the famous books. Okay, but I am going to follow this book, which is very good, and I found it very interesting to explain these concepts. Okay, now let us go up. We'll start with this. Any doubts, any questions up till this point of time? Please feel free to ask. Then we will move ahead, because we are going to shift now from statistics to probability. So I'll give a couple of minutes. If anyone has any questions, please feel free to ask now. Okay, it seems there are no questions. I'll move ahead. So while defining statistics, okay, while talking about statistics, we introduce these two very important terms. What are these terms? This is population and this is sample. What is this? This is nothing but the data. Okay, these are nothing but the data, right? So now we are going to go in depth for this, and we are going to talk about the process which generates this data. Okay, so the first thing that I'm going to define is an experiment. Okay, we will move slightly slowly, but we'll try to understand each and every concept. Okay, right. Experiment. So it may be a physical experiment, it may be a hypothetical experiment. Okay, and third most important thing is, okay, it may be a planned experiment, okay, and it may be a unplanned, if that is the right word I am allowed to use, unplanned, or what you can call it as natural experiment, where we don't have any control. Okay, so the physical experiment, I can give you some examples of this. Okay, this is nothing but tossing a coin. No concept in probability will go ahead without tossing a coin and throwing a dice. It's like when you teach simple harmonic motion, you have to use pendulum. Okay. In the same way, when you are teaching probability, you have to refer to these two very well-known examples: tossing a coin and throwing a dice. Okay. Right. Hypothetical experiment is selecting a number from 1 to 10. Now, this is a hypothetical experiment. I mean, you just imagine in your mind that there are 10 numbers, 10 natural numbers, okay, and you are trying to do the you are trying to select a number from this. Planned experiment, again, these are the examples of planned experiments, you can say. This is also an example of planned experiment. This is also an example of planned experiment. Next, we are talking about this unplanned and natural. So as I said, rainfall in Mumbai. Understand very important thing that each of these experiments, whether it is a physical, whether it is an hypothetical, whether it is a planned, or whether it's a natural where you don't have control over it, it is generating data. It is generating small data, moderate amount of data, or huge data, but it's generating data. Like tossing a coin is going to generate only two outputs, okay, which we call it as outcomes, okay, which is heads and tails. But each of these is going to generate data, and that data is going to be very important for that. And data science is what we are interested in learning. Okay, so we will move it. So first thing is experiment, right? Second most important thing is nothing but trial. Okay, what is a trial? Okay, so trial is single performance of the experiment. Single performance of the experiment. So you throw it once, okay, you toss a coin once, okay, right? Rains have taken place in the month of July, so we can talk it as a single trial, okay, right? We'll move ahead. Next thing what we are going to talk about is, so you have an experiment, you have a trial, which is the single performance of that experiment, and that trial of that experiment is going to generate an outcome, which is very important. Is going to generate outcome. Okay, so what is this outcome? It's very simple. For every trial, there is an outcome. Okay, so you throw a dice, you get an outcome. The number which is appearing on the top face, whether it's 1, 2, 3, 4, 5, 6. Okay, so this is what it is about experiment, trial, and outcome, right? And this is nothing but our data. This is nothing but our data. So this is what is my data. Okay, very important, right? We will move ahead. Next, we are going to define a very important. So what we are going to do? We are learning the set theoretic approach. So what is this set theoretic approach? The set theoretic approach says that can we use set theory? Can we use set theory to model an experiment, a trial, and outcome, and then the probabilities and other measures associated with this? Okay, so this is what is set theoretic approach. So what is the set? I think every one of you knows what is set. Set is nothing but a collection of. So basic example we can write down like this is set A is equal to 1, 2, 3. So this set contains 3 elements 1, 2, 3. So the idea is simple. Many of you might have realized now. So I'm going to collect these outcomes, okay, and call it as a set. I'm going to collect all outcomes. I'm going to call it a set. I'm going to look at the characteristics of some outcomes. I am going to call it as an event. And the moment I define event and sample space, I'm going to define a probability function. Okay, that is what we are going to do. We'll move ahead now. Okay, so now we are going to define sample space, very important concept. Okay, what is the sample space? Sample space is set of all possible outcomes of an experiment. Did we learn something related to this sample space? If you specifically look at this adjective all, set of all possible outcomes of an experiment. Yes, we learned something called as a population, which is not exactly as the sample space, but there is an analogy. Okay, you try to correlate the things. So you have a sample space, which is nothing but the set of or collection of all possible outcomes of an experiment. So if my experiment is coin, then my sample space is H comma T, heads and tails, because there are only two possible outcomes when you throw a coin, when you toss a coin. Okay. Second experiment is dice. Okay. Here, what will be your sample space? All possible outcomes. What are all possible outcomes? 1, 2, 3, 4, 5, 6. These are all possible outcomes of this. So you can, you can have any experiment. If my third experiment is a number, choosing a number randomly between 1 to 10, if that is my experiment, okay, the S will be 1, 2, up to 10. Okay, this is nothing but the outcome. Any of these can be outcomes. Okay, so this is how I define the sample space. Okay, now very important thing is this sample space, I will denote it by SS. Okay, it can be discrete. Okay, and it can be continuous also. Okay, this sample space can be discrete. Discrete means what? All the three examples that I have shown above. Okay, all these three examples, they are the examples of discrete sample space, where you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you can count it discrete. And there is another example which is continuous. We will not go into the continuous example of this sample space, because generally in data science, in machine learning, that means in reality, we don't consider this continuous data. We consider the data after some samples, or this is basically a discrete data. So we will talk about this discrete sample space only. We will not go into this continuous sample space. Remember, what is sample space? Sample space is the collection of or set of all possible outcomes of an experiment. Okay. Now here there are two types of this discrete sample space. One is countably finite. Okay. And another one is, countably infinite. Okay. So above three examples are the examples of discrete sample space. All the three examples that I have shown. Okay. All these three examples that I have shown, they are the examples of discrete sample space. Okay. And they are countably finite. Right? Because the number of elements in the set are finite. Okay. There is an end. Okay. Can you give me an example of countably infinite sample space? Basically, so we can have a very simple example here, that if my sample space is nothing but n, that is set of all natural numbers, what will be that? 1, 2, 3, 4, 5, and so on. Is this a discrete sample space? Yes. I design a hypothetical experiment that I want to choose any number, any integer randomly from a set of natural numbers. Then what will be, how many are natural numbers? Natural numbers are infinite. 1, 2, 3, 4, 5, 6, up to infinity. We don't know. Right? So, but are they discrete? Yes. Are they countable? Yes. But are they finite? No. So S is equal to n, set of all natural numbers, is an example of countably infinite sample space. Okay, again, this particular case is pathological to us, because we don't deal with infinite data. We deal with large data. We don't deal with infinite data. Okay, so this continuous is of no use to us. Okay, and this is also we are not going to use, but I just gave you an example that this is how you have this countably finite and countably infinite. Okay. So what is the thing that we have defined? Sample space. Okay. Sample space is what we have defined. We will move ahead. We'll define another thing. Okay. And the next thing that we are going to define, just a moment. Okay. Is events. The next thing that I am going to define is, I have defined sample space. I am going to define now events. Okay. Now what are these events? Sometimes we are interested in particular characteristics of the outcomes. We are interested in the characteristics of the outcomes. Now let me give you an example. We have this example of dice. Okay, my sample space here is set of all possible outcomes 1, 2, 3, 4, 5 and 6. Okay, right? Now I am interested in the outcomes which are odd. I am interested in all the outcomes which are odd. Okay, what will be that? So I'll define another set A which contains all the odd outcomes. What are these odd outcomes? 1, 3 and 5 basically. Okay, now here I am talking about a special characteristics, special property, okay, of the outcome, and you will immediately notice that this A is a subset of S. A contains 1, 3, 5 which are also present in your S. Okay, so we call A, A is a subset of S. Okay, and we call this A as event. So what is an event? An event is a subset of sample space with characteristics. So I may be also interested in all the all the all the outcomes in case of dice, okay, which are divisible by 2. So B will be, what will be my next event? 2, 4 and 6. I may be interested in the outcomes, okay, which are primes. So what will be my C? C will be, which are the prime numbers here? 1, sorry, 1 is not a prime number, my mistake. Okay. Okay. So 2, 3 and 5. These are the prime numbers. Okay. So like this, you can define all these events. Note that all of these are subset of this. Now event can be a singleton also. It can contain only one element. So I may be interested in an event which is nothing but just a number divisible by 4. So what will be my D? D will be nothing but 4 only. Okay. So event can be a singleton also. Right. So this is how we define event. And events, if you see, then it will click you that it is something similar to sample. Please don't misunderstand me that events mean samples. Not like that. Okay, we talked about population and sample. I'm just trying to relate here. Okay, so you have population here. Okay, which you can correlate, okay, with sample space. Okay, and you have sample which you can correlate with events. Okay, so we got this idea. Any doubts up to this point? You see what we are doing? We are modeling an experiment, a physical or a hypothetical experiment where the outputs are discrete and they are countable. We are trying to model it. We are going to give a mathematical representation to that in terms of set theory. This is what we are doing. Okay. Now, the next important thing that I am going to define is set of all events of an experiment. This is very important. Set of all events of an experiment. Now here comes the trick, and here comes a slightly difficult concept, because my events are basically sets. You agree? Events are basically sets. So I am talking here. So it is a set of all these sets. It is a set of all these sets. So I am talking about this sigma. Okay, I am talking about this sigma as set of sets. Okay, basically nothing to worry. It's not that difficult. What does this sigma contains? This sigma contains, it is a collection of all events. Okay, now what are the collection? What are all events? These are nothing but the subsets of your sample space. So let's take a simple example, coin example. Okay, let's take this coin example. Okay, so what is your sample space in this case? Heads and tails. Do you agree? Right. Okay, so this is your sample space. Okay, now how many events it will have? How many events it will have? So let's note down the events. Okay, right. First of all, the first event is S itself, H comma T. Every set is a subset of itself. So this is one thing. What is another event? I'll write it as A. A as only heads appearing. What is the third event? I will call it as B, which is only T appearing. And there is also a fourth event which we have to consider, C. It is nothing but an impossible event. And this is as per the set theoretic thing, and this is denoted by a set which does not have any element. So it is known as a null set. It is known as a null set, basically. So now this particular S has got these four events as subsets. Okay, right? And therefore I am going to write down sigma, which is nothing but the collection of all these events. Okay, so I'll start with the null set. There is one null set. There is only H, that is a singleton, a set with only one element. I'm calling it as a singleton. Then there is T, okay, and there is H comma T, which is my S itself. Okay, now please have a look at this very important concept. Okay, sigma is nothing but my set of all events. So sigma is a set. So what is sigma? Sigma is a set, okay, whose elements are sets. Why this concept is very important? Because the concept of probability that I am going to define, I am going to define on this sigma. I am going to define this probability as a function, or as a basically as a measure, okay, on this sigma. Okay, so I hope you have understood. If there are any doubts, please let me know. Okay, so what is it? So we have started. I'll just take a quick recap. Okay, So we started with the sample space, basically. I'm sorry. Okay. So we started with the sample space. Sample space is what? It is the set of all possible outcomes. Okay. Then we went ahead. We discussed about the types of the sample space. We are basically interested in this discrete sample space. Okay. And then we defined an important concept which is called as event. Event talks about the characteristics of the outcomes, and then we saw some of the examples of this. Okay, then these are some of the examples of these outcomes of this dice experiment, basically. So we wanted all primes divisible by 4 or all odd numbers or everything. Okay, right. Next we come to a very important thing, which is set of all events of an experiment. Okay, so and we denote this by sigma. Sigma is the set of sets. Okay, we move ahead and we define it. What is this? Sigma is the collection of all events or set of all events. Okay, and to start with, basically we have started with very simple example. S is equal to h comma t. This is coin experiment. So sample space is defined. There are only two possible outcomes, heads and tails. So we have taken heads, we have taken tails, and then we have defined the events. First event is the sample space itself. Okay, right. I am not interested in any characteristics. Anything comes, it's fine to me. So that is also one of the characteristics. So first thing is this S. Second thing is I am interested in only heads coming out. So this is a singleton. Singleton means a set containing only one element. Okay, H, which I denote by set A, then T, which I denote by set B, and third one is very important, which is an impossible event with the probability 0 that you will see. Okay, right? It is an impossible event, null set we talk about. And since these four are the events associated with this particular sample space, I define a sigma, okay, which is nothing but the collection. It is the set of these four sets. Okay, so this is my sigma. I hope you got the idea about this. Okay, now very important thing here I am going to define is the next thing. Before defining the probability, I am going to define something. Yeah, let's talk about something called as cardinality. Don't get boggled out because of these mathematical concepts. If we learn any concept in engineering without sound mathematical reasoning or understanding, then it becomes very sloppy. Okay, that is my very strong opinion. So I have decided to take you all on this ride of probability, and then through probability we will go to all these important concepts of expectation. I will not call it also as a mean, I will call it as an expectation. Okay, expectation, mean, mode, median, and all those things, standard deviation and all those things. Okay, right, fine. So cardinality in a very simple way, without adhering to too much mathematical jargon, I would define it as number of elements in a set. Of course, we are talking about countable and finite set. That's why I said that we are going to deal with only situations which are countably finite. Okay, number of elements in a set. Okay, now in our coin example, how many elements did this S have? S had two elements too. So I would say that. So I would say that cardinality of S is denoted as modulus of S. Okay, cardinality of S is nothing but 2. Basically, cardinality of S is 2. There are two elements. Can you tell me what is the cardinality of sigma? Sigma is a set of all events. Okay. Sigma is a set of all subsets of S. Sigma is a set of all subsets of S. Okay. So how many subsets your sample space has? 4. Agreed? Okay. And therefore your cardinality of sigma is also 4. It's just but the count. You just count the elements in a set. 1, 2, 3, 4, 5, 6. How many elements are there? Okay, there are 10 elements. You say that the cardinality of that set is 10. Basically. Okay. So this is also nothing but number of subsets of S. Do you agree? Cardinality of sigma is 4, which is sigma contains the subsets of S as its elements, and therefore the number of subsets of S which is equal to 4. Okay, and we have got a very important, interesting point here, that number of subsets of a set is equal to 2 to the power cardinality of the set. Okay, very important. So here S has got 4 subsets. Okay, it is nothing but 2 to the power cardinality of S, which is nothing but 2 to the power 2, which is nothing but equal to 4. Okay, just remember this. Why I am telling you this? Because the next example that I am going to take is about the dice. Okay, so let's take the next example as dice. I am explaining you the concept of events. Okay, right. Let's move ahead. See here, what is my sample space? What is my sample space here? The sample space here is 1, 2, 3, 4, 5, 6. Okay, right. Now the question that arises is, in this case, events. Shall we list down all these events? It will eat the complete time till 1 o'clock. Okay, right. We don't want to do that. So now this concept of cardinality will come. What is the cardinality of S? Cardinality of S is 6. So how many events this will have? Number of events. So how many number of events it will have? Okay, the number of events that it will have is 2 to the power cardinality of S, which is nothing but 2 to the power 6. What is that? 2, 4, 6, 2, 4, 8, 16, 32, and then 64. Okay, so there are 64 number of events, and therefore sigma will have 64 events present in it. Can we have a glimpse of the sigma? We will not write down all, but then you will have a null set here. You will have singletons. Okay. Then maybe you will have 1, 2. Okay. Then maybe you will have 1, 2, 3 like this, and so on. It goes on. Okay. Like this. Ultimately, you will have your S sitting here like this. Okay, so this is what is the set of all events of S when your S is the sample space when the experiment is throwing a dice. Is it okay? Very important. Okay, fine. So we have understood this. Now we are going to define the third very important one important thing that I would like to tell you here, which I should not miss. Okay, in case of this, in case of, it's better to explain this in this. Okay, now these two events, basically these two events, okay, which have got only one element, okay, they are known as primary events. They are known as primary events, basically singletons. Okay, so in case of this, in case of this particular thing, what are the primary events? What are the primary events? Primary events are when only you consider a set, you consider a subset of S where only one element is there. Okay, so 1, 2, 3, 6. Okay, so this is what is your, these are your primary event. So you take this one and you call it as one set. Okay, you take this and you call it as a second set. You take this, you call it as a third set, like that. Okay, so these are all primary events. Why this is important? You will realize this. I'll come to that as and when the situation comes. Now the thing that we are going to define, very important, is probability. Now probability is introduced as a function. It is introduced as a function. Basically, it is a measure. What is the difference between measure, okay, and function? There are some subtle differences, but which are beyond the scope of this. We will not go into those subtle things, those intricacies. Okay, we will talk about probability as a mapping or a function. So I hope all the audience, I mean majority of the audience, know about what is a function or a mapping. You have a domain, and then you have a range. Okay, just a moment, just excuse me for a moment. Yeah. Okay, so you have a domain and you have a range. Okay, and this domain contains some elements, let's say X. Domain is nothing but a set. This is also a set. Okay, then you select an element X here, okay, and some element here, right? Now you have a mapping which takes this F, okay, from the domain and gives me F of X. This is a function or a mapping. Okay, it's a very simple example. So my domain, to give you a very simple example, maybe a set from minus pi, okay, maybe my domain can be a theta which goes from minus pi to plus pi, okay, and maybe my range may be a set from 0 or minus 1 to 1, right? So can you tell me a function which takes values of theta from minus pi to pi and an output or an image in this set minus 1 to 1? Okay, I should have my mistake here. I should use these symbols carefully. Okay, so it should be minus 1. Okay, right. You have f of theta is equal to sine theta, or f of theta is equal to cos theta. These are the examples. So what they do, they take this theta from this domain, okay, or this domain, okay, and they give you answer, okay, which lies between minus 1 to 1. So this is the function, basically. So you know this. I mean, you have a lot of examples. You have encountered it, like cos theta, tan theta, okay, x square or maybe some other RAM function and all those things. These are all basically functions. So in the similar way, we are going to define this probability, okay, as a function, okay, or as a mapping. Now, very important thing here is you can have many to one. The mapping can be many to one. Many to one means there might be lot of elements present here which will map to a single one. Okay. But one to many is not allowed. You cannot have, I mean, you don't talk about one to many functions which are known as multi-valued functions. You don't talk about multi-valued functions. Okay, so let's leave this mathematics slightly apart. Okay, we are talking about probability. So let's take a quick recap of what we have done. Okay, so we have defined a sample space, and I'll take the example of coin h comma t. We have defined events. We know what are those events, and we have defined sigma, which is nothing but the collection of all events. So a null set, singletons or primary events. Okay, this is how we define. Okay, next thing that we are going to define is probability. Now, what is this probability? Very important. What is this probability? This probability, as I said, is a function, is a mapping. The probability is a mapping, okay, from sigma to the interval 0, 1. Okay, what is probability? So you have this sigma, okay, right? So you have this sigma, right? In our case, it contains only two elements, h and t. Oh no, it contains all these elements. What does it contain? It contains this null, then h, then t, then h comma t, okay, and then on this real line there is an interval between 0 and 1, okay, this particular, okay, right, and you define probability as a function which goes from here to here. This is how I define probability. Okay, because every event will have a probability. Every event will have a probability, and we know that probability cannot be more than 1. Okay, right. Maximum is the definite event which is going to occur. Okay, and in this case is our sample space. Okay, so we have, this is how you define the probability. So how do you write it? This is graphical representation. How do you write it mathematically? So probability, okay, is a mapping from sigma to 0, comma 1. I hope these things are clear now. Okay, right. Okay, so you define the probability like this. So in our case, what is going to happen? So you are going to find the probability of the null set. Sorry, you are going to find the probability of null set. You are going to find the probability of this primary event which contains only heads. You are going to find the probability of this primary set as which contains only tails, and you are also going to find the probability of your sample space. Okay, so this is how you are going to proceed in defining this this probability function. Okay, fine. So there are certain axioms, there are certain rules. Okay, there are certain rules which in mathematical terms you will call at axioms, which need to be satisfied by any function that is defining probability. Okay, right. So I hope this concept is clear about the probability. We are going slow, but I hope everyone is with me and you are understanding. Okay, so we talked about this. As I said, we talked about this sample space. We talked about event. So we talked about sample space. We talked about events, and then we talked about this sigma. Okay, and then we went ahead about probability. It's a function or a mapping from sigma, which is the collection of all events, to interval 0, 1. Okay, but any function cannot be a probability. It cannot be a probability measure, or it cannot be a probability mapping. The function has to satisfy three axioms, three rules basically. Okay, what are these? Those three rules we will write down. Okay, number one, if there is any event A which belongs to sigma, okay, then the probability of A has to be greater than or equal to 0. Very important condition. Okay, if you want to define, okay, the probability, and if you have any, so every event or every subset, what does this mean in plain English? Every event must have a probability. I mean, you cannot say that my sigma has got 10 events, okay, right? Out of that, only 9 has got probability. The 10th one doesn't have probability. No, that's not allowed. Then you can't call it as a probability function. Okay, right. This is one important thing. Second important axiom is, just a moment. The second important rule or condition is that probability of your sample space is always 1. Very important. Because what is sample space? Sample space is it an event? Yes, it is also an event. Okay, right. And it has got all possible outcomes. It has got all possible outcomes, and therefore its probability is 1. And the third important rule or axiom or condition which this probability function has to satisfy is slightly mathematical, but I am going to tell you. It says that if A and B are two events such that A intersection B is a null set. That means A and B do not intersect. They don't have any common element. If A and B, they are disjoint. A and B are disjoint. Their intersection is an empty set, a null set. Okay. Then it says that probability of A union B, union okay, is equal to probability of A plus probability of B. Very important. Okay, let me give you an example for this. First of all, you should understand this. Actually, this third axiom is it's a generalized axiom for n arbitrary events. Okay, but I have given it in a very simplistic way here. Okay, what does this say? Let's take this example of dice. This will be more clear. Or we can have a Example with coin also, not a problem. Let's say my A is a singleton H. Let's say my B is a singleton T. Both are primary events. Okay. Now what is A intersection B? A has H, B has T. So there is no common element. It's a null set. Do you agree? Fine. Now what does this axiom says? What does this axiom says? It says that, okay, probability of A union B. Let's try to do this. What is A union B? A is H, B is T. So probability of H comma T. You agree? Okay, right? It says that it is equal to probability of A, okay, plus probability of B, because they don't have any common elements. Okay, so it is probability of only H plus probability of only T. Okay, you go ahead with this. This is what you have understood. Actually, the theorem is more about A1 intersection A2 intersection A3 up to AN. It has got this particular statement, but we will not go ahead with this because this is slightly confusing. So I have given you a very simple example here. Okay, this is what it is. Fine. So now I think you have understood these three. So what are these three axioms that we have to consider? Please understand. Please let me take a quick recap of what we have done. So we have defined sample space, we have defined event, we have defined sigma, and then we have defined probability as a mapping. Okay. Probability we have defined as a mapping. Sorry. Okay. We have defined it as a mapping from sigma to this interval 0, 1. Okay. And then we have defined three rules. So I want to say that, okay, this particular P has got some rule, or I can come up with some mathematical formula, okay, for this. That's fine, provided it satisfies these three conditions. If it satisfies these three conditions, then and then only I will say that this probability function is a valid probability function, this function. Okay, right. So what is the first condition? Every event should have a probability, non-negative probability, I would call it. Okay, its probability can be 0 because probability of your null set is going to be 0, and this null set is an element of your sigma. Okay, right. Second thing is probability of the sample space is 1. Third thing is you define the probability, okay, for two sets which are disjoint, union of their union. So if A and B are two sets which are disjoint, whose intersection is an empty set, they don't have anything in common, then probability of A union B is equal to probability of A plus probability of B. Okay, remember very important thing, if A intersection B is not a null set, for example, if my A is H and my B is, let's say, sample space itself, okay, right, fine, then A intersection B, what is A intersection B? Is H. Do you agree? Because that's common. In this case, probability of A union B will not be equal to probability of A plus probability of B. Please note this. You have to note this very important thing. Okay, here this is very important condition. This condition is very important. Okay, so here A intersection B is not a null set. It contains one element H. H is the common element which is present in A as well as B. Okay, so intersection has got one element H. Okay, so probability of A union B in this case will not be equal to probability of A plus probability of B. This is this is an important thing. Okay, now let's go ahead. Let's try to understand something. Okay, now let's solve some examples. Let's try to solve some examples. Okay, now here very important thing, probability. Okay, is also defined, or it can also be understood in the terms of relative frequency. I'll give you a very interesting example about this. Lot of us, we may have some confusion or some very misconceptions regarding this. Okay, let's take this example of coin. Okay, what does it say? It says that the sample space is h comma t. Do you agree? Okay, now if I ask you a general question, okay, if I ask you a very general question that I have a coin, I throw it, what is the probability that heads will appear? And every one of us will give immediately answer that the probability is 50%, 0.5. There is a 50% chance that heads will come, and there is a 50% chance that tails will come. Okay, and this is how we try to relate the, this is how we try to define the probability. Remember, okay, we are going ahead with the mathematical definition of probability using set theory and all these things. Okay, but probability can also be defined as a relative frequency. Why I am slightly doing this deviation? I am doing this deviation because we are going to solve some examples. Okay, now here what happens is, when you say that when you toss a coin, the probability of getting heads is 50% and tails is 50%. Okay, because once you throw it, either you will get heads or tails. But things are not like that. What does it say is, throw coin for a large number of repetitions. What does this mean? This means that I will throw coin for say 10,000 times. I will throw the coin 10,000 times. Okay, then it says that every time note down the outcome. Okay, and let this be denoted by n. Okay, right, every time note down the outcome. If the outcome is heads, okay, you add that count in this nh. nh is the total number of heads appearing. So you throw it once, you get heads, you note down. You next time you throw it, you get tails, you don't note it. Next time you throw it, you again get heads, you note it down. So your nh goes on increasing. So you throw the coin 10,000 times, and in each of the trial, okay, you note down what is appearing, either heads or tails. Every time the heads appear, okay, heads appears, okay, you note down, and that number is your nh. Okay, right? Fine. Let's say consecutively 4 times tails appears. You don't note down. You note down only when heads is appearing. Okay, fine. Now probability. So this is a frequency based thing. Probability of heads is equal to NH by N, or I should say, I should be more careful about it. I should say here that it will approach to NH by N, or even more perfectly, I would say it is equal to NH by N. In fact, the definition of probability as a relative frequency, okay, is probability is equal to limit n tends to infinity, okay, n upon nh, basically. So the more you go on tossing the coin, the more this number will approach to 0.5, which is nothing but 50%. So in one tossing you get heads, in another tossing you get tails, and you say that the probability is 50% or 0.5. No, please understand this. What is happening is you throw the coin large number of times and you note down when the heads is appearing, and when that number is very large, maybe if you throw the coin for 10 times, exactly for 5 times the heads will not appear. Please note. Okay, if you throw it for 100 times, the NH by N will start approaching towards 0.5, but when your N is sufficiently large, very large, okay, it will start approaching this 0.5. It will start approaching this as your N tends to infinity. Very important thing. Okay, so why all this? Why this sudden digression from set theoretic approach to this probability with relative frequency and all that? Okay, we are going to use some formula to calculate it, and there we will assume that that relative frequency thing is available. Okay, so let's take this example 1. Okay, so we talk about this coin basically. Okay, here your sample space is your sample space is h comma t. Okay, and let's say you are interested in an event where your only heads is appearing. Okay, right. Now how do you find the probability of A? The probability of A is defined, okay, or I will give you a general formula. Okay, the general formula is, and this is the formula that we use. Probability of an event is equal to cardinality of event upon cardinality of the sample space. This is the formula that we are going to use. But we will always keep in mind this important concept. We will always keep in mind that probability defined in this way is basically a probability based on relative frequency. Okay, right. We will move ahead. Okay, so now I want to find, so what is the cardinality of the sample space? Cardinality, as we know, is the number of elements, 2. What is the cardinality of your A? Is 1, because A has got only one element. Okay, and therefore the probability of A is equal to cardinality of A divided by cardinality of S is equal to 1 by 2, which is equal to 0.5. But don't forget this important part. Don't forget this important part. Why I have introduced this example suddenly? Because everything was in Greek and Latin, very abstract mathematics. We are engineers, so we should get. If we don't play with the numbers, okay, we start feeling uneasy, isn't it? So just to give you some idea about this, we have. But remember, this particular set theoretic approach, okay, is what we are going to do ahead, and we are going to go ahead with this. Okay, right, fine. Let's move down.
Vishwesh sir,
Yeah. Yes, sir.
would you like to take a break for some time?
I'll just take one example and I'll take a break of 5 minutes if that's okay.
Okay, sir. Okay. Go ahead.
I'll just take one example and then I will announce a break of 5 minutes.
Okay, sir.
Yeah, thank you, sir. Thank you. Okay, let's move ahead. Okay, so now let's take the example 2 of dice. Here the situation is slightly more interesting. Your sample space is 1 to 6. Okay, so cardinality of S is 6. Okay, now you want to go ahead and you want to find the, let's define an event A where odd number appears. Okay, odd number appears. So A will be equal to 1, 3, 5. Okay, and cardinality of A will be equal to 3. Okay, and then we will go ahead, we will find the probability of A is equal to cardinality of A divided by cardinality of S. Sorry. Okay, which is equal to 3 by 6, which is equal to 0.5. This is how you define the probability. Just give you an example. Okay, maybe we can take a break here. It's 11:38. Maybe we can join, or I'll just explain one important concept. Okay, and then we'll take 11:40. We will take a break. I will explain to you something called as joint probability. What is a joint probability? So A and B are two events. Okay, so I am interested in the probability of their joint event. Probability of A intersection B. Okay, probability of A intersection B, which is equal to probability of A plus probability of B minus probability of A union B. Do you recall this, dear participants? If you recall this, this is one of the, this relates us to our probability as a measure. This is the third condition. Okay, if A and B are disjoint, then this will be 0. Okay, right? And we will get just probability of A intersection B. Okay, oh no, that was another formula, my mistake for that. Okay, so this is an important formula about probability of A intersection B. Okay, right. So here I can write down, still we have the hopes. Okay, so we can write down probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Okay, now if your A intersection B is a null set, in this case you have if you have this, if your A intersection B is a null set, okay, then its probability will be 0. You see that therefore probability of A union B is equal to probability of A plus probability of B. Okay, right. So we will take a break here. We will resume at 11:45. Sir, is it okay?
Yes, sir. Yes, sir.
Okay, sir. Sir, can we start? There is one question by one of the participants, Ms. Aparna. We use tools like SAS, R programming for statistics. Is there any such tool available for probability? Uh, of course, there might be some tools available. I am not aware of that, any computer tool or any software or anything. Okay, but what we are learning is more of a mathematical background of probability. Okay, things will fall in picture. Okay, once we go ahead with this standard deviation and all those things. Okay, so right now it's like, I mean, matrices have got, I'll just give you an analogy. Matrices have got a lot of applications. I mean, you can't imagine any engineering field or mathematics without matrices. Okay, but at the back end, what is there? It's a linear algebra, isn't it? Okay, so something similar to that, set theory. So we are using this set theoretic approach for the probability. I hope I have answered your question. If not, please let me know. Okay, we will resume. Am I audible?
Yes, sir. Yes.
Is my screen also visible, sir?
Yeah, it's visible.
Okay, thank you, sir. I'll resume. Okay, so let's have a quick recap, and if we have any questions, please let me know. It may happen that participants may find it slightly mathematical, but yeah, it is mathematical, but you will see that as we will move ahead. I'm going to introduce the next concept of random variables. Okay, and maybe if possible in this lecture or the day after tomorrow's lecture, we will the next thing would be very fast, that you would be able to understand very fast as related to all these basic concepts. Okay, right. So if there are any questions, please let me know. You can post them in chats also, and uh, okay, fine. So there are no questions coming here. We will move ahead. Fine. Next, let me give you an example. Okay, again, something called as conditional probability. So we introduce this joint probability. Now we will introduce something called as a, just a moment. Yeah. So the next thing that I'm going to introduce is conditional probability. Very interesting. Okay. This is also a part of our curriculum for this FDP. Okay. Now, let me first write down the definition. Okay. Let B is an event such that probability of B is greater than 0. Okay. So B basically B has a non-zero probability. Okay. Right. Then probability of some another event A provided B is equal to probability of A intersection B divided by probability of B. Now, first thing is very important is this is not same as probability of A. Basically, in both the cases, in this case also and in this case also, we are finding the probability of A only. Okay, but the situations are different. What is the difference? In this case, I am finding the probability of A with no condition. Here I am finding the probability of A when B has already occurred. Event B has already occurred. Okay. So what does this mean? What does this mean? This means that B has occurred. Okay. Now, what is the probability of A? B has occurred. B has already occurred. Now, what is the probability of A? And that's why in the numerator, this A intersection B term is coming. Very important. Okay. So let's try to understand this. Let's try to understand this with the help of an example. Okay. So let's take our well-known example of dice. So let's take an example of dice. Okay. So your S is nothing but 1 to 6. Okay. Right. S is nothing but 1 to 6. Okay. Now let's say A. A is any event. Let's define it as the number which is appearing is, you throw the dice and the number appearing is divisible by 3. So what are the outcomes? What outcomes will A have? A will have naturally 3 and 6 because these are the numbers that are divisible by 3. Okay, right. I want to find the probability of A. I want to find the probability of A. Okay, let's just find out the probability of A. What will be the probability of A? It is cardinality of A divided by cardinality of the sample space. So cardinality of A has 2 elements. So this is 2 divided by this is 6. This is 1 by 3. Do you agree? Okay. Fine. You get this cardinal. This is the probability of A. Okay. Next, we take an example. Okay. Now I want to find out probability of A when B has occurred. When B has occurred already. Okay. Now in this case, let us define B as any odd number. Okay. So you have, so what will be your B in this case? Your B will be 1, 3 and 5. Now the question that you want to ask when you want to find A given B or conditional probability of A when B has occurred. Now the point is your event B has occurred. Event B has occurred means any odd number has come. Now what is the chance, what is the probability that that number will be divisible by 3? Okay, so when B has occurred, you can say that either 1 has come or 3 has come or 5 has come. Now out of this, what is the probability that that number is divisible by 3? So we know that this is the number, okay, which satisfies this basically. Okay, so let's try to use our formula. Okay, so we will find out A intersection B. A intersection B is 3. Okay, and then we find the probability of B, because we need that in formula. Where we need it? We need it in this formula. Probability of A intersection B divided by probability of B. We need it here. Okay, right? So probability of B is cardinality of B divided by cardinality of S, and this is equal to 3 divided by 6, which is 1 by 2. Okay, right. Next thing we find out A intersection B. Which is my A? Which is my A? This is my A, and this is my B. Okay, I'm trying to find out A intersection B. Obviously, the A intersection B will be only 3. Okay, right. Now, what is the probability of A intersection B? Probability of A intersection B is cardinality of A intersection B divided by cardinality of S. So this is 1, because it has got only one element, and this is 6. 1 by 6 basically. Okay, right. Now I'm going to find probability of A given B, which is equal to probability of A intersection B divided by probability of B. Now probability of A into B, okay, is equal to, there is a slight delay in this, so I'm sorry for that. Okay, okay. So what is probability of A intersection B is 1 by 6 divided by probability of B, which is 1 by 2, which is equal to 2 by 6, which is equal to 1 by 3. Now you may think that what is the difference? Okay, because the probability of A, absolute probability you can call it, okay, has come as 1 by 3, and this has come as 1 by 3. This is the coincidence. Okay, but remember, the concept is totally different. This talks about A when B has already occurred, and this talks about just the probability of A. Just the probability of A. Okay, right. We'll move ahead. So I hope things are clear now. Fine. This is just to give you just a flavor of this. Okay. Next thing that we are going to consider is statistically independent events. Okay. I am going to talk about statistically independent events. Okay. Right. The idea is very simple. What does this mean? A and B are SI. I am writing it statistically independent. If, in plain English, what does it mean? Occurrence of A have no effect on B, and vice versa. Do you agree with this? Okay. What is the second way, right? Or tell it in mathematically. Okay. What does it mean mathematically? Mathematically, it means that probability of A given B is equal to probability of A. Very simple. Okay. So probability of A given B, conditional probability. So A does not depend on B. So whether B occurs or not, whether B takes place or not, has no effect on A. So probability of A given B, or conditional probability of A given B, is equal to probability of A. Now if we substitute this, okay, here we get an interesting relationship. What is the relationship that we have? Probability of A given B, okay, is equal to probability of A intersection B divided by probability of B. Now this is particularly this thing. This is basically equal to this. Okay, so if I substitute this here, what I get is probability of A intersection B is equal to probability of A multiplied by probability of B. Okay, this is an important condition for statistically independent events. Okay, please note. Okay, right. Next thing I'm going to tell you, now we are going to come back. So let's take a quick recap of what we have learned. Okay, let's take a quick recap of what we have learned. Okay, so we learned about sample space, we learned about events, okay, then we learned about something called as probability. In between we learned about this sigma, okay, right? And then we learned about conditional probability. We learned about joint probability. Okay, while explaining these three concepts, we have used the set theory for understanding this. Okay, now we will try to go ahead and we will try to understand combined sample space. Combined sample space. For example, two experiments are combined. After this, we are going to go to random variables. Okay, examples I can give you. Tossing a coin plus tossing a dice. I mean, you can also do an experiment, right? You throw the dice and you toss the coin simultaneously. That can happen, right? And then you are interested in the combined outcome. Now you are interested next in the combined outcome of that. Okay, so you are interested now in combined outcome. Okay, very important, combined outcome. Okay, so in the first case, in this case, what is your sample space? I will denote it by S1 now. H comma T. Okay. In this case, what is your sample space? 1, 2, sorry, just a moment. There is a slight delay in my pad. Okay. Just a moment. Okay. Fine. Yes. Rub all this. Okay. So you have coins plus dice. So for this, S1 is equal to H and T. For this, S2 is equal to 1 to 6. Okay. Now your S, that is a combined sample space. S is equal to S1 cross S2. What does this cross means? This cross means pairs. This cross means pairs. Okay. So how will your S look like? Now you imagine you have thrown a dice and you have thrown a coin and you have thrown a dice also. Okay. So you are getting head and you are getting 1. This is one outcome. Then you are getting head and you are getting 2. Like this, head comma 6, right? Then you will have T comma 1, T comma 2, okay, up to T comma 6. Okay. So now here you can define an event. What event you can define? Let's say I define an event A which says that getting heads plus even number. Okay. So what will such event look like? Tell me. You get an even number and you get heads. So A will have H comma 2, H comma 4, H comma 6. Right. So this is how you have your event defined. This is a combined sample space. For this also you can find probability. Just think about how its sigma will look like. What is sigma? Set of all events. How it will look like. Okay, just imagine that. Okay, right. Now I am going to introduce for the last 40-45 minutes or 50 minutes. I am going to introduce you to a very important concept, and that concept is of random variable. Okay, so let's go ahead with this about the random variable. Any doubts, any questions till that point, till this point? Let me check the chat box. Okay. If there are any questions, I would request participants to that we can have discussion on it right now, because now I am going to go into random variables. Now it's very interesting topic, slightly mathematical. okay, but very easy to talk. But it makes everything very easy, and then everything will fall in line. Once we finish the random variables, then we will introduce all these notions, these expectations, average, mean, mode, deviations, and all those things we will introduce in terms of random variables only. Okay, right. Let me check the chat again. Okay. Fine. Let's move ahead. I think there are no questions. I hope all are not, I mean, we are not saturated. Okay, the probability of getting saturated after a 3 hours probability lecture is 100%. Okay, so let's make sure that we don't get saturated. Okay, you should be always have rigorous mathematics done before you embarking on any study of any subject. That's what I feel. Okay, right. So now let's introduce something called as random variable, abbreviated as RV. Okay, now please note that when we talk about random number, it is just any number. So I mean to say the average income of any person in Mumbai is a random number. Okay, or randomly if you pick up some person and if you measure the height of its hand, his or her hand, okay, it's a random number. They are called random because they cannot be predicted, right? Now a random number is a truly random number. Okay, you cannot predict it. You don't know which number is going to come. Okay, for example, if you want to get an idea, the output of a chaotic system is a random number. You don't know when it is in the chaotic mode. It gives you a very random output. Okay, what these softwares are generating are basically pseudo random numbers. Python, MATLAB, pseudo random numbers. They are random numbers, but they are pseudo. Why pseudo? Because there is an algorithm used to spit out that random number, to generate that random number. But when there is an algorithm, you know which random number which number is going to come next. Okay, they are pseudo random numbers. Of course, they maintain all those properties that it is Gaussian and it's normally distributed and all those things. Okay, right. Let's move ahead. Okay, our random variable, what we are going to talk about is totally different. Is totally different. Okay, from random number. Is totally different from a random number. Okay, the random variable that we are going to talk about, it is a mapping or a function. Now already we have introduced one mapping as probability. What is probability? Probability is a mapping from your sigma to this 0, 1 interval 0, 1 on the real. Okay, right. Probability is a mapping from sigma, right? Now what is this sigma? Sigma is the set of all events. Agreed. Okay. Now you are saying it looks slightly confusing. So already we have introduced one mapping or one function which is from the set of all events, that is sigma, to this interval 0 comma 1. That is fine. Now why you are coming up with one more mapping or function? It is becoming more complicated. That you will understand the importance of this random variable concept or this notion, okay, when I tell you the next thing. Okay, what is this mapping? What is this random variable? I'll write again. Random variable is a mapping, okay, from, now the most important thing, which is the domain and which is the range for this. Okay, random variable from S, your sample space, to R. What is R? What is R? R is set of real numbers. It is a set of real numbers. So we have one mapping probability which goes from sigma to 0 comma 1, and we have a random variable x. It is denoted by x. Remember, even though it looks like a variable, or it is also called as a variable, it is basically a mapping or a function. Okay, a random variable is a function from S to R, set of R real, all real numbers. Very important, these two concepts you should note down. Okay, why they are very important? Okay, why? I mean, first of all, you should understand the difference. So for this, for probability, sigma is your domain. Okay, and your range, the output value you will find in 0 comma 1. In case of this random variable, okay, it has got a, it takes the values, or it takes the arguments from your sample space, and it spits the answers in your R. Okay, right. Now, why are we? Very important question. Why random variable? Why to introduce random variable? Did you notice very important thing? Your S can be very different for each experiment. I should use the word not only S, nature of S. Nature of S can be different for each experiment, right? For example, if you take coin experiment, the sample space is h comma t. Do you agree? If you take the dice experiment, the sample space is 1 to 6. Okay. If you take the card experiment, drawing a card randomly from a well shuffled deck of 52 cards. Okay. What is your sample space here? Here sample space are physical objects. So you get king of spade, okay, queen of spade, okay, then you will get jack of heart, okay, so and so on. If you take another experiment, okay, for example, height, sorry, okay, so if you take an example of height, measuring the height, So S will have some numbers 1.3, 2.7, 5.8 and all those things. Okay. If you take an example, okay, or if you take an experiment of, let's say, let me give an example where there are physical elements present in a sample space or hypothetical elements present in a sample space. Okay, for example, let's say you try to find out the phasor of voltage. Okay, right. Then maybe your sample space will have some complex numbers 3 plus J4, 5.5 minus J 6.7 and so on. Okay, right. Let's say you try to find out the how much is the angle between two fingers of a person. Just hypothetical. The forefinger and the middle finger, these two fingers. Okay, this is forefinger, this is middle finger, and you try to find out this angle theta. Okay, your sample space will have angles in degree, say 20 degree, 50 degree, 17 degree, and so on. Now, what you have understood here is that your sample space may have physical objects, it may have numbers, complex numbers, angles, real numbers, heads, tails, and everything. It may be present. Okay. Now, look at your random variable. What this random variable is doing? This random variable, okay, is basically is a mapping from sample space to R. So ultimately, if you define a proper random variable, okay, irrespective of what are the outcomes present in your sample space, okay, you can always represent them with some numbers. Are you getting what I'm trying to say? So in this case, if I define a random variable such that x of h is equal to 0 and x of t is equal to 1. If you define this, then this sample space can be represented by simple numbers 0, 1. In this case, there is no issue. I can define the random variables as x of s. S is an element of this small s, okay, as s itself. Okay, in this case, look in the third case. What is happening? In this case, I have physical objects as my sample space. King of spade, I have a card. Okay, jack of spade, jack of heart, the physical object. Okay, here I can define a random variable x acting on s, small s. What is this small s? This small s is an element of this sample space. That means it is an outcome, and I can assign some number to it, small number x. Okay, then this complete sample space which I have here can be nicely represented in terms of some numbers which are real numbers. Are you getting me? Okay. In this case, again, there is no problem. In this case, yes, my sample space can be represented by some real numbers. Okay, right. So this is the advantage of sample space. Okay, just a bit. Okay, so this is the advantage of sample space. The advantage of sample space. So I hope you have understood the importance of sample space. Advantage of the random variable. The advantage of and random variable is sample space can be mapped to real numbers. In other words, I can become more detailed and I can say that every outcome of SS can be represented by a real number. Very important. Every outcome of a sample space, can be represented by a real number. Now that makes my things very easy. That makes the whole affair very easy. Why it makes the whole affair very easy? Because now whatever may be the outcome, once I define this function or mapping, okay, and I represent them with some real numbers, I have to deal with only those real numbers. So I have to forget whether my sample space has got physical cards, as I said, jack of something. Okay, I don't have to worry about that because I know that this particular number in my new sample space, which contains all random variables, okay, it has got one interpretation as actual outcome in the sample space, but now I am using it as a number. I am representing it as a number. Now the next thing that I have to do is number crunching. I have to just use those numbers, isn't it? So I have defined sample space. Okay, so what next? I hope this is clear. Okay, so sorry. Okay, so by defining a random variable, okay, what is happening is sample space has real numbers as elements. Sample space has real numbers as elements. Okay, right? And therefore events, sigma, and probability, okay, can be defined on this sample space with real numbers. Do you agree? Very simple. Okay. So this is how you define. This is the importance. This is the motivation of introduction of this concept of random variable. Okay, it's a function. So let's go ahead with the formal definition. Okay, so x, okay, is a function goes from S to R, complete set of real numbers. Okay, so if there is an outcome small s belonging to sample space, okay, then x of s, x acting on s, x is a function, remember it's a mapping, it takes this outcome from a space, okay, nothing but a real number. Okay, so pictorially if you want, may make idea clear. So this is my sample space S. Okay, this is this small s sitting, and this R. Okay, I will define a random variable. Okay, so this s will go to some number here, which is nothing but x of s, and this is a real number. This is a number. 0.3, 1.2, minus 2.3, whatever it is, it's a number. Okay, all right. I hope this diagram makes the things clear. Okay, let's take some example. There are some conditions for a function to be random variable. Okay, we will go to that later. Right now, let me give you some examples which will make your concepts clear. Okay, right. So example 1. Okay. So our coin experiment, S is H comma T. Okay. Right. Ah. Now we define an RV such that I'm defining the random variable, I'm defining the function. But what do you mean by defining? I have to give you a rule, okay, which will map each outcome of this sample space, okay, into a number, real number. Okay, right. So I define it such that x of s is equal to 0 if s is equal to tails and it is equal to 1 if s is equal to heads. Very simple definition I have given. Okay, what does it tell me? It tell me that if my s, which is an element, which is an outcome of the sample space, if it is t, okay, give me the output as 0, number 0. If it is h, give me the output of as 1. So in other words, x of t is 0, x of h is 1. Okay, right. So now the most tricky part comes. Can I write my sample space as now just 0 comma, sorry, can I write my sample space as just 0 comma 1? Answer is yes. Why yes? Because this sample space, which had some elements as H and T, which were the outcomes of this coin throwing, coin tossing experiment, okay, now they have been represented by numbers 0 and 1. Now tell me which set is easier to handle, HT set or this 0 1 set? Obviously this set is easier to handle. But now when I say that my sample space has an outcome 0, you should immediately understand, you should look here, and you should see that yes, when I say 0, 0 means my actual outcome that I am talking about is tails. When I say 1, then actually I am talking about heads. Basically, things will become more clear when we will take another example, example 2. Okay, example 2. Okay, our S is now throwing a dice. So 1, 2, 6. Now here my sample space already contains numbers. So there is no problem. There is no problem in that. I can define a random variable for this as I can define the random variable if S small s belongs to capital S, then x of S is equal to S by 2. This is how I define the random variable for this. So what will be my values? What will be the images of these values here? This is the random variable function or random variable. I will not use the word random variable function. Random variable is a function. So whenever I use the word random variable, you should immediately understand that this is a function basically. Okay, so x of 1 is 1 by 2, which is 0.5. X of 2 is 2 by 2, which is 1, and so on. Okay, and so on. I will not go into this. So what will my new sample space look like? Is 1 by 2, 1, 3 by 2, 2, and 5 by 2, and 3. This is my new sample space. I can also define x of s as s itself. There is no harm in that because these s are only numbers only. Okay, this I can define it. So in this case, my sample space will be original 1 to 6. Okay, I can also define x of s as s square. I can define anything unless and until it satisfies some axioms that I am going to tell you. Okay, I think this makes the concept clear. Okay, right, about the random variables. Okay, now the most important thing, and things start becoming slightly tricky and therefore interesting also, is the interpretation of events. Interpretation of events in terms of RV. Okay, in terms of, this is very important. How do you interpret events in terms of random variable? Okay, this is very important. So that's what we are going to see. Okay, so I'll take an example. Okay, about our experiment only. Okay, start with the simple one, h comma t, and we define the random the way we have defined it here, like this. This is how we define the random variable for this. Okay, and we have the new sample space as 0 comma 1. Now can you tell me what are the different events here? A, which is a null set, which is also a null set in terms of random variables. B, which is h, so in this case it is 1. C, which is t, which is nothing but 0 here. D, which is nothing but my SS only, so h comma t, so in this case it will be 0 comma 1. So you have defined events. Now note on this side. Okay, these are the events that are defined, okay, when you have already defined a random variable. Very important. Okay, I hope things are clear. Right. Next we are going to define sigma. So what will be sigma in this case? Null set 0, 1, 0 comma 1. Actually they are null set h, sorry, t, h, and h comma t. But now since you have defined random variable, you will be using this definition and this representation only. Okay, right, fine. Next, take our coin example. Okay, here this example will be used, okay, to explain to you how the events can be written in terms of when the random variable is defined. So let's take this dice example. Okay, so S I know 1 to 6. Okay, fine, no problem. And I define a random variable x of s as, say, s square. So what will be my new s? Tell me. 1, 4, square of each outcome. 9, 16, and 6. I hope clear now. This is my new sample space. Okay, now I define an event A, okay, right? The number appearing is less than or equal to 4. I throw the dice, the number appearing is less than or equal to 4. Okay. In conventional way, how you will define this event? This is an event A. This is an event A. How do you define this event A? Okay, this event A is defined as in the with the conventional, with the original, not conventional, with the, this is my original sample space. This is the sample space SS with RV defined. Okay, right? So original, in case of original sample space, this event will have outcome as 1, 2, 3, 4. Do you agree? Fine. This is okay. Now, how do I define this in terms of in terms of the defined random variable? Sorry. How do you define it? After the random variable is defined, you will write it as 1, 4, 9, 16. Is it okay? Fine. Now I am going to write it in a different way. This is such that this contains all the outcomes small s, which are the elements of S, such that S is less than or equal to 4. Do you agree with this? Very important definition. Okay, so A is the event which has got a characteristics that the number appearing on the dice when it is thrown is less than or equal to 4. So A can be written as 1, 2, 3, 4 for the original sample space, and it can be written in this set theoretic abbreviation or set theoretic crisp representation as S. It contains all S such that S is less than or equal to 4. Now, how do I write it here? How do I write it here? Okay, I can write it here as, okay, all those x of S such that, okay, x of S is less than or equal to 16. Do you agree? Do you agree with this? X of S such that x of S is less than or equal to 16. Is it okay? Right? Have you understood this important way of describing the event? Because I have defined a random variable based on this. Okay. Is it okay? Fine. We can define it like this. Now, this A is nothing but, okay, all x of I am writing it again. Okay, x of S which is less than or equal to 16. I will write it in a different way. I will now do one thing. I will now do one thing. Just wait. Okay. I will now drop this. I will drop this. I will now no longer write this. I will write it as x of S less than or equal to 16. Okay. So this means this. Means this. Means this. Means this. Are you with me? Okay. So note this. So you have a number event A appearing which is less than or equal to 4. You write it like this. Then you write it like this. Okay. Then you, after defining that random variable, okay, as a square of every outcome, you write it as x of s is less than or equal to 16. Then you drop this, and then you even further drop this argument s. You don't show this because it's not required. So you write finally a as x less than or equal to 16. This is how you finally define your. So this is the most simplistic way to define an event using RV, using random variable. Remember, all these A's, all these A's are same. Just the notation is different. Just the notation is different. Okay. They are one and the same thing. I hope I am making sense, and I hope everyone is with me in defining this particular event. Okay, I am going very slowly. Okay, we will cover up in the next lecture, not a problem for that. Okay, but these things are very important, and one must understand these concepts very clearly in order to go ahead. Okay, have you understood this? Very important. Now, had I defined this random variable in a different way, let's say if I had written like x of s is equal to s cube, okay, or sine of s, I can also define x of s as sine of s. I can define taking s as in radian. I can do anything. Okay, then appropriately these things will change. These things will change. Okay, so this is how you define a random variable. So the moment I say, that a is equal to x less than or equal to 9, okay, immediately we should be able to do the back interpretation in a way that this is nothing but x of s less than or equal to 9, which is nothing but equal to all s such that x of s is less than or equal to 9, or all x of s such that x of s is less than 9. So x of s, okay, so this is nothing but 4 and 9, okay, which is nothing but equal to all s such that s is less than or equal to 3. So basically this is nothing but 1, 2, 3. Okay, this is very important. So what you should understand is how do you define a random variable. Very important. Okay, so this is how you define from here, you go to here and back like this. This is how very important. So do you agree that by introducing the notion of random variables, defining an event has become very easy and it has become very crisp. It has become very easy to define this, very crisp, easy, isn't it? So this is how you define these events in terms of this. Now I am going to give you a general definition, okay, Let me use this pen. In general, okay, an event is defined in terms of an RV as A is equal to x less than or equal to small x. Now this small x is nothing but your variable. Is nothing but a variable. Okay, this is how you define the random variable. Okay, now let's take one more example. Let's take one more example. This time we are having a hypothetical experiment. Okay, choosing a random number randomly between 1 to 10. Okay, choosing a number randomly between 1 to 10. Okay, so S is nothing but equal to 1 to 10. Okay, and I define x of S as again S square in this case. Okay, so my S will be equal to 1, 4, 9 up to 100. Do you agree? Okay, now I define an event B which is equal to all numbers between 3 and 6. All numbers selecting or choosing randomly numbers between 3 and 6. So what will be in case of original sample space, what it will be including 3 and 6. So 3, 4, 5 and 6. In terms of random variables, how this will be? This will look like, this will be like 9, 16, 25 and 36. Okay, now I can also write this B as 9 less than or equal to x less than or equal to 36. This is how I am going to define this particular event. Remember, this is same as this, which is same as this, and which is same as this. Are you understanding what I am trying to tell you? Okay, this is how you define the random variable. Okay, now I will quickly tell you about the two conditions, okay, on a which a random variable has to satisfy. Okay, you can have any function as a random variable. See, we use any mapping. Sometimes we considered S square, sometimes we considered S cube, sometimes we considered S by 2 or anything. Only that there are two conditions that need to be satisfied. Okay. Before I tell you these conditions, okay, I have to tell you one important thing. Okay, the important thing here is now we define probability on these new structure of events. So what does this mean? This means that in this case, probability of B, okay, I can directly talk about probability of the B, or I can directly talk about probability of B. Both should give me same answer. Very important. So I will write probability of, how do they write in a typical probability book or how they follow it? Probability of 9 less than or equal to X less than or equal to 36. They define it like this. Okay. So probability of x1 less than or equal to x less than or equal to x2. This is how you define the probability, or you define the probability of x less than or equal to x directly. Remember, immediately when you encounter such type of notations, you should understand that this is my event. This is my event, okay, which has been mapped under a suitable definition of random variable, okay, and now the event has got a probability because events are the elements of your sigma and probability is the function which is defined from sigma to interval 0 comma 1. Okay, this is how you will have to do it. Okay, I hope this makes the things clear. Okay, now we will talk about two conditions. Okay, first condition on the probability function, or the, if you want, not probability function, random variable function. If you want a mapping or a function to be eligible as a random variable, okay, it says that probability of x equal to minus infinity is equal to 0, and probability of, second condition, x equal to infinity is equal to 0. Okay, these are the two important conditions which the function has to satisfy. We will right now not go into the meaning of this. Okay, I will tell you when we will talk about other advanced concepts of this. Let's not worry about these conditions. Just remember this. Okay, these are some of the conditions. Okay, it's almost 1 o'clock, but I will take 5-10 minutes more and I will try to tell you something about this. Okay, so let's take a quick recap of what we have understood. Okay, so we have understood experiments, then we have understood outcomes and trials, then we have understood events, then we have understood set of all events, in the meantime we also understood cardinality, then we understood probability, as a mapping. Then we understood conditional probability. Okay, there is a slight delay in this pad. Fine. Okay. Then we understood joint probability. We have skipped Bayes theorem and all those things. Permutations and combinations I will take in the next class. Okay. Then we understood random variable. Okay, right? And then we understood events and probability with an RV defined. Okay, these are some of the things that we have understood up till now. Okay, the next thing that we are going to talk about is the distribution function. Very important. Okay, now slowly we have started moving ahead into the various you can say indices, if that is the right word, if I am allowed to use various indices and various properties which will give me the information about the data. Okay, right. So its full name is cumulative probability distribution function, but it's more popularly known as distribution function. Okay, right. Now, event can be defined as A is equal to X less than or equal to X, small x. Do you agree with this? X less than or equal to small x. Okay, right. This is how you define an event. Now here you will find that this X is nothing but a variable. Why? Let me explain it to you. Okay, this is your sample space. This is your R. Okay, and you have this random variable X defined here. Okay, right. Now, if you are talking about an event X less than or equal to 0. Okay, this is your 0. What this will be on the real line? It will be this particular part. Do you agree? All this. Okay. Next, I talk about, just a moment. Next, I talk about the event as the event as X less than or equal to 1. What is this? This is your 1. Okay. So now you consider this complete. Next, I talk about X less than or equal to 2.7. What is this? This is, let's say, 2.7. Okay. So this is the complete. Okay. So ultimately, your X is nothing but, so when you talk about an event X less than or equal to X, okay, this x is a variable. You can treat this as a variable. It's not a variable. You can treat this as a variable. The moment you change your x, okay, the number of outcomes present in your event will change, and therefore its probability will change. Do you agree with this? Okay. So the point here is, I'll just take last 5 minutes, then we will wind up. Okay, this is an important concept. Okay. So here, as x changes, number of outcomes in the event change. Okay, and as the number of outcomes change, okay, the probability also changes. Do you agree? Okay, so I am making a statement now. For an event x less than or equal to x, okay, okay, probability of this event depends on x. Very important. Therefore, this probability is a function of x. Very important. This probability is a function of x. Okay. So I will denote it as f x of small x is equal to probability of x less than or equal to x, basically. And this is nothing but my distribution function. This is my distribution function. Okay, so you have a look at this. Mm, So you have a look at this. As your x changes, there are more either the events are, either the outcomes are added or outcomes are subtracted. If you move in this direction, outcomes are added. If you move in this direction, outcomes are removed, are excluded from your event. And if an event contains more number of outcomes, then its probability will increase. If an event contains less number of outcomes, its probability will decrease. And therefore, the probability is the function of this x. Basically, you see from where we have started from the experiment, sample space and all that. Then we came to the random variable, and with the random variable we have been able to describe or define this distribution function. We will stop here now, okay, because it's 110. I think we all are saturated, might be saturated. Okay, I hope you understood. It may sound mathematical, nothing to worry. In the next class, day after tomorrow, that is on 23rd, I'm having sessions from 10 to 1 again, and then 5 to 7. So that 5 hours I will in for 2.5 hours I will talk about the remaining part of this probability and statistics, and the remaining part 2 hours or 2.5 hours I will talk about the tensors. Tensors are also important in machine learning and data science also. Okay, they are advanced versions of your vector space, your vectors and matrices and all that. Okay, so I'll be talking that in the next thing, but we will continue from where we have stopped. In the same sheet, I am going to continue in the next lecture. Okay. Nothing to worry if the thing has become very heavily mathematical. It's not very heavy mathematics, but if you feel in spite of that, nothing to worry. You just understand this. Okay. Maybe what I will do, I will share this. This is in Microsoft Whiteboard. So I will share this. It can be saved as a JPEG. I will share this with Rathod sir, and I will request Professor Rathod sir to share this with all the participants so you can have a recap of what has been covered. Okay. So with this, I come to I come to the halt here. Okay. I'll check if there are any questions. Okay. There is one question about confirm second condition. Okay. So let me check what is the second condition. It has been asked by Dr. Chetana, I think. So let me check it, madam. If I made a mistake, my apologies for that. Just a moment. Okay. This board has started behaving weirdly. I think it was also not ready for such heavy mathematics, it seems. Okay. I think the second condition is this only. But if there are any mistakes, I will cover x equal to infinity, and these are the two conditions only. Okay. Anyway, we will see. Fine. We can stop here, sir. I think there are no more questions. I'll stop sharing my screen.
Yes, sir.
So
Yes, sir.
there's one more question actually.
Yeah, please.
Uh, Manoj sir is asking about probability x equal to minus infinity equal to 0. What is meant by this statement?
I will explain. I will come to that in the next class.
Okay, sir.
It
Okay.
requires some understanding about this distribution function and all that. I'll come to that. That's what I said. For the time being, nothing to worry about that. I'll come to that. Okay.
Okay. Thank you so much, Dr. Vishwesh, for this wonderful session on probability, and we learned a lot of concepts in a lot of detail from you. So I would like to summarize this session by saying mathematics is not only about numbers, equations, computations, or algorithms. It is also about understanding. Thank you, Dr. Vishwesh, for making this understanding so easy for all our participants. I'm sure all participants learned a lot and thoroughly enjoyed your session. Thank you once again. Now I may request Dr. Rathod for any instructions to the participants.
Yeah, ma'am, please. Thank you, sir. Thank you, Vishwesh sir. So we will meet again day after tomorrow. Yeah, day
it's
after
my
tomorrow.
it's my pleasure, sir. It's my pleasure.
A very nice session, sir. Very nice session. We will
Thank
meet,
you.
and for entire days, your session is there. Day
Yeah,
after tomorrow.
yeah.
Okay. So thanks a lot. We will meet on that day.
Okay.
And for participants, other instructions are like this. Evening, there is a session by Rocky sir. So please, whatever instructions he has given yesterday for the installation purpose, Google Colab, you remember. So please complete that. Otherwise, you will be in a trouble because he wants you to complete that installation, right? You remember yesterday's session. And those who have joined newly, because what I did is we found out that there are few participants who are not giving the quizzes, or they are not attending. They are not attending. So there was a queue in waiting. So we have allowed them, and we took them inside this workshop, because even though 2 days are over, but there are so many days to go. So why to lose their learning opportunity? So I welcome all the other participants who have joined us today, and I request them to go to the YouTube link which is given in your invitation email. Please see that, and please refer your earlier sessions also. The days which you have missed, they were wonderful sessions. First day session and the second day also from the S.K. Gupta sir and the entire mathematics. So you please refer those sessions. It is my sincere request. And no more new entry will be allowed in this workshop. Even if somebody comes with a request, we are not going to allow, particularly for FDP1. Okay. And those who have missed the quizzes, we will see what is to be done for that, for the new participants. So don't worry about that. But tomorrow onwards, you have to please give the quizzes. We have created all the Moodle logins now. There is no issue as far as Moodle login is concerned. But still, if you have any issue, if anybody is facing any issue, including new participants, so please let us know. Our organizing committee will solve it immediately. One most very sincere request to everybody. Quizzes are online. When you are giving a quiz, at that point of time, do not put anything on your WhatsApp chat, on WhatsApp group. It is an examination and you all are teachers, so you can understand the meaning of that. Correct? Don't put, we believe you, that you will follow all those ethics, which we tell our students regularly. So do not put questions there, answers and the queries. If you have any doubt in any question, afterwards you can discuss with our people, no, those who are experts. I told on the first day itself, who are handling the assessments and the lab sessions, correct? We have Nikat madam, we have Pallavi madam, we have Varsha madam, we have Soni madam, we have Renuka madam, we have Aparna madam, and we have Pramod sir also. This entire team, we have a backup from the IT and computer department, and I'm really thankful to all of them to handle your queries on day-to-day basis. So you can get to them and you can solve your questions, answer. If you are not satisfied with the options, you can tell them and they will answer your questions. But do not post the messages on WhatsApp group during the quiz. Correct? And my sincere request is that. And anything else? No, nothing. If you want to ask, you can ask. Otherwise, we will meet in the evening at 5 p.m. Okay. And please rename yourself in this account. If somebody is logging with the administrator name, from the first day we are telling that don't put your name as an administrator, it creates a confusion. And I'm writing here continuously that don't put your name as an administrator, and please reply back what is your name. But I'm not getting reply, so that means you are forcing me to expel from this meeting. Right? I can do that. I'll block your entry. If you want me to do that, I'll do that. But otherwise, please tell us. Acha. Your name, A. Rao. Okay. Ma'am, please note this name. So, but I don't know why you are not able to rename yourself. But I understood now what is your name. Okay. So, thank you very much. Thanks a lot. Okay, we'll meet in the evening if you don't have any doubt. Thank you, sir. Vishwesh sir.
Thank you, sir. Okay sir. I'll quit, sir. I'll quit the meeting, sir.
Yes, sir. Yes, sir. I am also stopping the meeting. It's done.
Okay.
Thanks.
Thank you,
sir.
Thank you, sir. Thank you. My pleasure.
Okay, sir.